Today is Neural Net Day and SVM Day, Support Vector Machine Day. For those of you with a mathematical background, this will seem a little informal. For those of you without a mathematical background, it will seem intensely mathematical. But my focus is going to be on the intuitions. And for those of you without a mathematical background, there'll be some mathematical asides for the cognoscenti, but mainly I want to do the intuitions, because if you get the intuitions, you'll know more about these methods in a practical sense than a lot of people who are mathematicians and have followed the mathematical steps but don't have a feel for why these things work and what they do and where there have been happy mathematical accidents and all of that sort of thing. So that's a mathematical perspective. There's another perspective, and that's the why did AI people do this? Well, first of all, AI people did not do support vector machines. That's done by theoreticians. Why am I talking about it today? Well, because support vectors work on the kind of problem that AI people are expected to know something about solving. So AI people who want to be worthy of the name have had to incorporate an understanding of these machines into their repertoires, even though it's not stuff that was developed by AI people. So it's another case where the technology has been borrowed and stolen. But AI people did develop neural nets because, in the end, we are the smartest things around. And if you open up our heads, you'll find that they're stuffed with neurons. And so it would seem that neurons have something to do with thinking. And therefore, if we could understand how neurons produce thinking, then maybe we wouldn't have to, maybe we could all go home. Now, I don't know why you've all been here this whole year, because if we're to understand computers, surely what we want to understand is semiconductor physics. And once you've understood semiconductor physics and know how transistors work, then everything else can be sort of figured out from there, right?
Of course.
A computer is stuffed with transistors, so transistors must have something to do with computing, so all you need to do is understand the transistors and you can go home. That's the way I think about neural nets to some extent. Yeah, they enable thinking, but they're not what thinking is about. Thinking happens at another level. Nevertheless, having said all that in derision, neural nets are good for something. They're function approximators. And they're function approximators that can be used for classification. And right now that's all gobbledygook, but by the end of the morning you'll know what I'm talking about. And then you'll see that support vector machines are also good for classification. And you'll see that in certain ways they're superior to neural nets for doing classification. So that's our agenda. And I'll show you some demonstrations of both neural net function approximators and classifiers, as well as support vector machines. Well, why neural nets? Because our heads are stuffed with neurons, and maybe if we could copy or mimic or simulate what goes on in a neuron, we could do magic with it. So what's a neuron? Well, from the perspective of a computer scientist, a neuron is a cell body, an axon, and a whole bunch of processes, as they say, that is called the dendritic tree. The dendrites go back there. And so out here, it might be that the end of an axon connects to a dendrite of a following neuron and tickles it a little bit when there's a pulse that goes down the axon. There's a little gap there called the synaptic gap. This thing over here acts sort of like an adder. It adds up, or probably, actually I shouldn't say it's an adder, but it's a combinator. It combines the influence of all the ticklings that go on in the dendritic tree to help the neuron decide if it wants to fire a pulse down the axon. And that's an all or none sort of thing. You either have a pulse or you don't. If there is a pulse, it travels down the axon, maybe gets divided up in this smaller axonal tree and tickles some downstream neurons. So how can we capture that in a model that we might use computationally? Well, one way is to do it this way. There's a incoming influence, which we'll call x. Maybe there's another one, x2, and on the way down to xn. Each of these influences gets multiplied times some sort of weight. What, W1, W2, and on down to Wn. And that's meant to mimic what goes on at a synaptic at a synapse. Depending on the strength of the synapse, the influence may or may not get through. So there's a weight. And then to combine everything, well, there are lots of ways to combine things. You could do it with a logic table, or in the case of the usual kind of neural net, you can do it with a little box that just adds everything up. That corresponds to sort of what the combination of the dendritic tree and the cell body does. But then we have to decide whether a pulse gets fired or not. So let us put this result, this sum, through a box that performs a thresholding operation. So
those weight x's are not the same x, right?
These are all different x's.
But the other x's inside the circles.
Those are multiplication signs. Maybe better to use the computer science kind of multiplication sign. Those are multipliers. So the sum is compared with the threshold, and if the sum is greater than the threshold, then the axon is the simulated neuron is said to fire, and a 0 or a 1 comes out depending on whether you're greater or less than the threshold. So this is a model of a neuron. Is it a good model of a neuron? Gee, I doubt it. It's a model that's better to say is inspired by neurons, but it's not a model of a neuron. If you say it's a model of a neuron, it's a vulgarization of what a real neuron does. We don't know how a real neuron computes and whether all of the little peculiarities of neural activity are artifacts of biological hardware or essential to the computation. We don't know how important the synapses really are. And we don't really know if the synapses are where most of the interesting action is. But nevertheless, from the point of view of the AI gang, this is a model inspired by, most would say it's a model of, I would say it's a model inspired by biological hardware. So, what can we possibly do with such a thing? Well, we can use it for computing something and maybe classifying something all by itself. After all, what we're really doing here is we're saying that there's some output, z, which is equal to, which is determined by whether some weighted sum, wi times x of I, we add all that up and we compare it to a threshold, t, and our decision rule is that if it's bigger than t, we say 1, and if it's less than t, we say 0. But we can certainly think of those x's as the coordinates in a feature space. So what this is really doing is checking to see whether this weighted sum of coordinate values is more or less than t. At the decision point, where that sum is just equal to t, we have an equation that looks like that. And from high school geometry, we know that's the equation of a straight line. So in this space of x1 and x2, what a single neuron is actually doing is performing a computation. It's doing a decision based on whether or not you're to the right or to the left of that straight line. And that's all that a single neuron of that shape can do. So it's a classification process. Now it's also a function approximation because this sum will give us an output for any set of x's that come in, not necessarily just zeros and ones. It happens that this one will give us just a 0 or 1 out, but there is some function computed here, and it could be an approximation to some other function. That's why we call it a function approximator. And by adjusting these weights, we can get this single neuron to approximate a variety of different functions. But no one would be interested in this technology if computers were able only to simulate a single neuron. People are interested in this technology because you can put lots of these things together and get fancier decision boundaries, fancier ways of classifying the inputs into various yes or no results. So you can think about that, you can sort of sketch that out on the back of an envelope as you got a bunch of x's coming in to a bunch of neurons, and I'm just going to make this highly schematic. These are all connected together in various ways with those weighted lines. They may be sparsely connected, they may be completely connected, but anyhow, out here comes a bunch of y's, y1 to yn. So for any combination of x's coming in, some nx's coming in, we can produce some m's coming out. So it's a function. It's a function of many variables. It's a multivariate function. Because these things are thresholded, these values y through ym are going to be either zeros or ones. But there are a lot of continuous values in here where we're multiplying zeros and ones times a variety of weights. Now, of course, what we may want is we may want these y's to be trained up. We may want the network to be trained up so that on a training set, the y's are close to some desired y's. We assume we've got a big pile of already classified data for which we know what the y's ought to be. And so we can compare the actual y's coming out of this network with all of its inputs and all of its weights with the desired set. And once we've got the thing adjusted so that these are good approximations to each other, then we can unleash this neural net on some stuff of unknown class, and it will tell us what it's been trained to tell us on the training set. And the training set will determine what it tells us when we hit it with a real unknown. So if we want to be mathematical, we would say that there's a vector y, a whole bunch of individual y's, that is a function of a whole bunch of x's, the input vector x. But that's not all it's a function of. It's a function of a weight vector, all of the weights that are buried in here inside of the individual neurons. So what training consists of then is adjusting these weights so that the actual y's are close to the desired y's for the training set. What does close mean? Well, you have some measurement of how close things are, and that's your performance metric. So if we march in here now and say, well, let's, if we're going to understand this, we're going to have to understand it in a simple situation first. We can say, let us make our simple situation just a situation in which there are only two w's. So we can have a space that has w2 over here and w1 over here. And our performance, that is to say how close the actual outputs are to the desired outputs for a training set, will be determined by the combination of w1 and w2 that we happen to be currently using. So in general, this performance will be a function of the w1 and w2, so there'll be some kind of surface in this space. So what we really want to do is we want to adjust w1 and w2 so as to get to the high point on that surface, maximum performance, closest approximation on our set for a sample set. Everybody with me so far? It's just intuition, right? No math yet. Well, how could we get there? We already know. We've talked about search. One simple-minded way of doing it is just to use hill climbing. We adjust each of these a little bit along the coordinate axes, and we evaluate the performance at these 4 new points. We see which produces the most increase in performance, and we go that way. So in other words, if we look down instead of to the side, if this is W1 and this is W2, and we start out here, we might follow a path that looks like this as we seek the maximum in performance. All we're doing is we're taking one step in each direction. We're evaluating this as yet unspecified performance function at each place, and we just keep marching in the direction that improves our performance. And improving our performance means that on the training set, the zeros and ones desired are close to the zeros and ones produced by the network. You now understand how neural nets work. How is it that thousands of papers are published on this subject? Well, because there are fancier ways of doing the hill climbing. And in fact, there's a breakthrough sort of mechanism that was discovered a while back called the backpropagation algorithm that made these things practical. Why is it not practical without it? Well, because this is 2 dimensions, so you've only got 4 places to try. If you got 100 W's, a 100-dimensional space, that's, too many places to try. So you want to have a better way of climbing the hill. And that's where we separate ourselves from the basic intuition and start talking about the math.
So the pure gradient methods are 2, because the space might be highly non-convex.
No. We're going to use a gradient method. We're just not going to. We're just not going to take steps along the coordinate axes. We're going to take a step in the direction of the gradient. Jeffrey, right. What Jeffrey has pointed out is that the mathematicians have given us a way to do this kind of search that's better than just blindly trying a step along each of the coordinate axes. We step in the direction of the gradient. What's that? Well, the intuition is here's the performance measurement, and suppose we determine that if we march along W1, the performance metric gets really good fast. But if we march in the direction of W2, it doesn't seem to make much difference. If I were to say that to you, and let us go back to our original position. If I were to say we get more good out of going in the horizontal direction than we get out of going in the vertical direction, then you'd be inclined to take a step that's mostly in the horizontal direction. So if the rate of change of the performance measurement is greater for a horizontal step than for a vertical step, you'll go mostly in the horizontal direction. So how do you express rate of change? Well, our calculus instructors say that we write it as the derivative of the performance with respect to a motion in that W1 direction is an important thing to know about. If that's big, if the performance changes a lot as we move along that axis, then we should move mostly in that direction. And if we write the step that we take in terms of movement along the W1 direction and movement along the W2 direction, then this specifies the step that we actually take. So if what we learn is that there's a big rate of change in this direction and a little rate of change in that direction, we'll go mostly in that direction. And that direction will be specified as this much in the W1 direction and this much in the W2 direction. And that's called the gradient. To put it in the mathematical lingo for the mathematicians, we're taking the partial derivative with respect to each of the variables, and we're taking a step that's dictated by the size of those partial derivatives. Right? So what we can say then is that the change in the weight vector is equal to some rate constant r times this gradient. And this is what the mathematicians tell us is the way to climb up a hill. Too bad for our side, we can't use it. Not yet, anyway. For one thing, Annoyingly enough, we can also vary the thresholds as well as the weights. So that's a pain. But there's a trick we can use to get rid of the get rid of the thresholds. What we're going to do is we're going to uniformly use a threshold at 0 so that our box now looks like this. And the way we're going to do that is we're going to add another input pegged at -1 multiplied by the threshold t. Now t is just like any other weight. It's just a trick where we've taken a number out of that threshold box and put it into another sort of virtual weight. So now this becomes just like any other weight. In fact, I'll just call it W0. And that can vary just as these other weights can be varied. So now we've done one nice thing. It helps condition the problem for mathematical treatment. But unfortunately, it's not enough. There's one more thing we have to do that the mathematicians demand of us before we can use this gradient ascent trick. Jeffrey, do you know what it is? There's something wrong with this network. There's something wrong with this function that prevents us from using gradient ascent.
Oh, because of it's an inequality constraint?
No. What are the conditions on the shape of the hill that you're climbing?
You have to know that a global maximum and a local maximum are...
Unfortunately, even when we're all through, there may be local maxima problems. Gradient ascent only works if the space has a certain property.
That's a gradient.
It has a gradient, or in other words, it's continuous.
Right. Yeah.
It has to be continuous. What that means is that if you make a small change on the input, you get a small change on the output. If you make a small change in the input, you get a small change in performance. If it doesn't have that continuous property, you can't use gradient ascent. And unfortunately, this threshold operation is not a continuous function. So what we have to do is we have to make another change to our original formulation to deal with that. We can't have that step function in there. So what we do instead is we make one more change in which we basically smooth out the step, make it look like that. And we can do that, if you want to know the details, right? You can do that by saying that the output is equal to e to the input over 1 plus e to the input. And I think about that a little bit and I say, oh, is that right? Yeah, that's right. Let's see if it makes sense. If I is very big, if the input is very, very big, then this will be e to the I over e to the I. It'll be 1, just as I require out here. If e is very, very negative, then this will be 0, as I require out here. If e is equal to 0, that'll be equal to 1, so it'll be 1 over 1 plus 1, so it'll be 1/2. So I have, in fact, got my formula right. So in these two steps, we have conditioned our original vulgarized neuron so as to make it, so as to put it in a form that's mathematically more tractable. So in some sense, if you follow that so far, all you need to know, all you really need to know, is that by making those changes, we can condition the learning problem to be a problem in gradient ascent, where mathematics, where a mathematical formula tells us how to make changes in the weights in order to get better performance most rapidly. Okay?
The performance is a match between the output and the criterion?
The performance is a measurement of how close the actual outputs are on a sample set of desired outputs. But we really ought to say something about what that is. In fact, we ought to really follow this all through the simplest possible neural net. And when I do this, I'm expecting this to be an aside for poets. But for mathematicians, I'd like to just show you a little bit about it so you can see what the other steps are. All right. So what I'm going to do is I'm going to draw on the board the world's simplest neural net. There'll be no thresholds. There are only 2 neurons. It's going to look like this. There's x getting multiplied times W1, producing a product P1. It goes through our threshold box and produces y. Y is multiplied times W2, which produces P2, which again goes through a threshold box producing z. And z goes through a box to produce a performance measurement. And the performance measurement is going to be this: z minus d squared. So we don't have vectors anymore because we have vectors with only one thing in them. So we're really talking about scalars, not vectors now. But we're using the standard distance metric. We're calculating the distance between the vector distance between the desired value and the actual value, and we're squaring that. Now, squaring it does 2 things for us. It means that it's bad to be off either way, but more importantly, it makes the mathematics tractable. You often see that kind of performance measurement because it makes the mathematics go through. And actually, what I'm going to do is I'm going to put do one more thing, put a minus sign out there. A lot of people talk about gradient descent. I like to talk about gradient ascent, so that when you go up, it's better for you. So this, if this is perfect, then z is equal to d, and that's 0. This quantity inside the parentheses, squared, gets bigger the further you are from being right. So that makes it more negative. So you get the best you can be with this performance measurement is 0, and everything else is increasingly negative. So we're trying to climb up to 0. Now, the mathematicians have to watch me carefully because I screw this up 45% of the time. So let's see, what do we need to do? We need to figure out how much we want to wiggle W2 and how much we want to wiggle W1. Now, let's do a little bit more intuition before we go into the math. If increasing W2 a little bit does a lot of good on this performance measurement, then we want to do that. On the other hand, if increasing W2 or changing W2 doesn't have much of an influence on our performance measurement, then we want to leave it alone because it might screw up some other things. So, in other words, we want to, if wiggling this causes a good change here, then we want to increase it, or we want to change it. Maybe that making this, maybe the change this down does you a lot of good out here. But the amount of change we do ought to be proportional to how much good we do. That's the whole idea. And so now the magic of partial differentiation and chain rule takes over and translates our intuition into some mathematics, so we know exactly what to do rather than just intuitively what to do. So basically, what we want to know is how much P, the performance, changes as we wiggle W2. Okay? Well, because we have had our freshman calculus course, we know that we can use the chain rule on this problem and express this relationship in terms of the intermediate variables. So we can write that as partial of P with respect to Z times the partial of Z with respect to W2. That makes sense, doesn't it? What it says is that if we want to find out how much this changes with a change in this, we can find out how much this changes with respect to a change in this, and then multiply that times the change relationship downstream. So in the end, it does make sense. But this is not an elementary calculus course, so I won't try to develop that intuition. But the fundamental intuition is still, we're trying to make the changes that do us the most good on our performance. Now, the partial of the performance with respect to Z is something we can actually calculate. Right? That's minus 2 Z minus D. So that part's done. But now, partial of Z with respect to W2, that's too hard. We're going to have to use the chain rule again and say, well, that's partial of Z with respect to P2, partial of P2, that product, with with respect to W2. Now P2 is equal to the product of these. So we can do that differentiation. That's just going to be equal to y. Oh my god, though, this one, partial of z with respect to P2. We've got to find the derivative of the output of this box with respect to the input. And that's where doing that, I got to say, this wasn't just randomly picked out of the air. There are lots of functions that look like that, but this one is really beautiful because the relationship between the input and the output, the derivative of the output with respect to the input, is gorgeous. It just turns out that partial of z with respect to P2 is equal to z times 1 minus z. It's amazing, isn't it? The derivative can be expressed entirely in terms of the output. It's gorgeous. You could say it's a mathematical trick. It's a mathematical sleight of hand. It's a selection that is within the envelope of reasonable things to do that happens to make the mathematics work nice. So let's see. Oh my God, we're done. We've got everything. So we're on a roll, right? Might as well do W1 too. And it's not just because we want to play with the chalk. It's because we want to discover something about the relationship between these derivatives. So let's see. Partial of p with respect to W1 must be equal to the partial of p with respect to the partial of z, partial W1. So I'm just going to work my way back. So we know that. That's minus 2 times z minus d. Now we got to do this. Well, that's partial of z with respect to P2, partial of P2 with respect to y. Oh, wait a minute. We know that. That's z times 1 minus z. Partial of P2 with respect to y. Let's see. If I did, I'm sorry, not yet. Partial P2 with respect to a partial W1. Partial W1 with respect to partial P2 with respect to W1. There we go. Finally got it right. That's I'm still within the 45%. Okay, partial of P2. See, what we're trying to do now is figure out how much this wiggles when we wiggle that. So we've got to break that down again. That's partial P2. Let's take it one more over to partial y with respect to W1. So this is the output of this with respect to that, and that's just W2. Phew, I'm still doing okay. Now we want to take this with respect to W1, so we have to do the chain rule yet again. That's partial of y with respect to P1, partial of P1 with respect to W1. This is that input-output relationship again, so that must be y times 1 minus y. And partial of P1 with respect to W1, that's x. I think I got it right. But now, whenever you do this sort of thing, you have to kind of stand back and look at it a little bit. And when you do that, you say, well, wait a second. To do this downstream one, I had to compute something here that I've already computed, because these are the same. And similarly, these are the same. And generalizing, what you discover is that much of what you have to do in each layer depends on stuff you've already done. So in the end, the amount of work you have to do is a linear function of the depth of the network, not a horrible exponential function. So the way we've done this, the way we've set the problem up, the way the layers interact, the mathematical discovery is there's a way of adjusting these weights that's a linear function of the number of layers. And that's the magic. of the so-called backpropagation algorithm. So to complete this demonstration, if we now still look at this a little bit and say, well, what depends on what? We can see that W2 depends on Z. W2 depends on Y, like so. And the extra stuff that W1 depends on is W2 and Y. Oh, no, is that, no Y, no Y, no. W1 depends on W2 and on X. Sorry, and there's the Y, and on Y. So if I were to continue this back 100 layers, instead of just the minimum to show you what goes on, I get the same pattern repeating all the way back 100 layers. I get the same dependence of the derivatives on local stuff and stuff I've already computed. That's why it's linear in the number of layers. Okay? So every once in a while something good like that happens in mathematics. It doesn't happen often. But when it happens, it's glorious. Fast Fourier transform is an example of the same sort of reuse of computation.
That depends on that formula at E to the I.
Jeffrey asked if it depends on this formula. Not fundamentally. That just makes the mathematics a little prettier, but the local relationship holds no matter what that function is. It just makes the math a little prettier, but it is not fundamental to the idea. This was considered a discovery by the people who figured it out, that there was a way of training up a neural net to bring, there was a way of mathematically determine how to adjust the weight so as to bring the desired outputs more into alignment with the actual outputs. So, who needs anything more? Let's do a demonstration. Let's have a look at one of these things at work. Now, let me say that this is sort of where you start, but there have been hundreds of people working on this for hundreds of years, or maybe thousands of people for 10 years. I'm not sure which. So, as you might imagine, there are many, many variations on the theme. You can have feedback loops, you can have different kinds of functions, you can have different kinds of performance measurements, you can have different kinds of boxes here and there, but it's all sort of the same, and the kind of results you get, the kind of phenomenon you witness, are not particularly dependent on the exact details of the formulation. So what I'm going to show you is actually a demonstration with another form of neural net that I cooked up called that's based on some work by Tommaso Paglia, a form called radial basis functions. So it's just an alternate way of constructing a network like this. But it has the same sort of general properties. So what I show you will be true of what we developed here as well as the Paglia network. Function. I know what it is. It's a secret. I'm not going to tell the neural net what it is. I'm going to let the neural net try to approximate it. And once the neural net has learned to approximate a function, then it can, you can say, well, I'm going to put on top of that a classification mechanism so that if the function's above some value, then I'll say yes, and if it's below, I'll say no. So a function approximator becomes a classifier just by comparing its output, comparing the output to some threshold. But fundamentally, we're talking about something that's good at approximating a function. So what I've done is I've sampled this function at 3 places. Those red dots on the red line is the function that is my secret, and I'm telling the neural net that the output is given for 3 values of the input. And what I'm going to do is I'm going to try to take steps in the gradient direction so as to bring the neural net into good alignment with the truth. So let me take, let me just take a step. Let me initialize this. There's my first step. I had the rate constant cranked up a little bit. That's why when I originally took this step, it went a lot further than I expected. So the amount of change is going to depend not only on the gradients, but on that arbitrarily selected rate constant. So if I take another step, another step, another step, another step, another step, you see how it's sort of kind of trying to bend its way into an approximation of that function.
Where is it even getting these lines?
Well, what it's doing on each of these iterations is it's comparing the green line, the current output of the neural net, with the 3 points on the red line, and it's taking steps in the weight space so as to make those closer and closer.
And it's generating those lines by some...
Oh, and those lines are just the complete function, not just for the 3 points, but they're the whole function generated by the neural net. So for every x, you're getting a y.
How big is the net?
This network has 3 neurons in it. So let's take some more steps. Let's take 10 steps. Let's take 10 more. 26, 27, 28, 29, 30. So there's 30 steps. Got some ways to go. Let's take another 20. So you can see with each step we're getting closer and closer. Let's take 20 steps. So it's just trying like mad to get the green line to go through the remaining red points. It's pretty close now. Let's keep going. Okay, so it's 100. Let's go to 150 steps. Okay, so now it's pretty close. But notice one thing. In the vicinity of that second red point, the green line has had to contort itself quite a bit in order to get close to the red dot. That's okay. It's got the degrees of freedom it needs to get close to the red dot, but it's contorting itself a lot to do it. And if I let this thing contort itself too much, it will faithfully come close to the dots, but it won't be a faithful approximation to the green curve. This is called the phenomenon of overfitting. You've got enough flexibility in the system that you're training to train exactly on the trial data, but in contorting itself to fit that trial data, it may have to go all over the place in between the data points. So if I came in with a unknown value and wanted my system to give me a result based on the training set, and if my unknown value were at this point on the x-axis, then I will do increasingly badly the more I train the net. So overfitting is a real problem with these kinds of things. But that's not the only problem. Let's go back and start over. But now let's crank up the rate constant a little bit. It's awfully slow, and you say, well, you know, let's do it faster. Let's use a bigger rate constant, so we'll use bigger steps. We're going in the same directions, but we're going to take bigger steps. So you'll see immediately that 20 steps here gets you does a lot of good. Let's take another 10. So in 30 steps, we're done just about as well as we did with 150 or so with a smaller rate constant. So if a bigger rate constant is good, then a still bigger one must be even better. So let's initialize it and take 20 steps. That was great. Oh, what? Is this a bug in my program? Certainly not. I've tried it before. What happened?
Overshot.
It overshot. Why did it overshoot? It went unstable. The rate constant got up so high that it was overshooting and basically creating a positive feedback loop.
Was it actually unstable, or was it just not convergent?
It was actually unstable. You see, it's all over the place. It'll never converge, and it just keep blowing itself apart. So therefore, you can use this stuff, sure, but there are several cautions. One is, and you've been mystified by it, I can sense it. Whatever your problem is, you gotta represent it as a bunch of inputs, and you gotta interpret the outputs. So if I say I want to give you a problem that's equivalent to identifying animals at the zoo, you've got to translate all the properties of the animals into zeros or ones on the inputs, and interpret the outputs as yes, it's a cheetah, or it's that, or something else. So interpretation is one big problem with a neural net. And much of whether you're successful or not successful with a neural net depends on how you do the interpretation. Another problem is you've got to be careful about your rate constant. In fact, there are all sorts of sophisticated schemes that vary the rate constant so that you don't get into these unstable situations but can still make progress. But the big problem is overfitting. And here's what happens. If you choose too many, if you stir into your mix too many neurons, too many weights, too many things that you can vary, in other words, if the number of degrees of freedom, the number of weights, is too great, then you can easily get into this overfitting phenomenon, because when you get a lot of weights, you can make a surface that curves around a lot, and in its zeal to fit, it will overfit. So, what are you going to do? Well, one thing you can do, and you must do this. You can't use a neural net unless you use this. Is you divide your training data into 3 bags. So all training data is divided into 3 bags. I guess this looks like a bag. I've never tried to draw a bag before. There's 3 bags. This is the one you train with. This is the one you test with. That's natural. The other thing you do, though, is you have a stop set. This tells you when to stop. So what you do then is you use this to train, and every time you've done a chunk of training, you try your neural net on the stop set. And as long as you're improving, then your performance on the stop set should go up as you train. But there'll be a point when you start to overfit, and then your performance on the stop set will go down. Because in your zeal to contort your surface to fit the training set, you're going to be off on the stop set. So this is a piece of data that prevents you from getting into those overfitting situations that I illustrated on the screen. And then, because you want to evaluate everything when you're all done, then you've held out some test data as well. But the stop set's important. Yeah.
So how much of this comes from these neural net guys talking to the defectors of went from AI to statistics? Because a lot of this.
A lot of these guys who do this work are statisticians wearing AI clothes. They're numerical analysts who are interested in optimization. They're the custodians of knowledge about various ways of climbing hills and spaces, more sophisticated than we talked about here. There's gradient, conjugate gradient, and all sorts of mechanisms that you can use that are more sophisticated. Now you wouldn't actually want to implement any of this stuff yourself. You go buy somebody's shell that had all this stuff built in. So what we've done today is now you've seen what's under the covers of those things and why those products are shaped the way they are, the kinds of features that they offer, and so on. But it's good stuff. It function approximates, and you can use the function approximation to classify. But there's some problems. There's the overfitting problem. There's the interpretation problem. And there's the rate constant problem.
Any big successes?
Are there any big successes? Neil asked if there are any successes, and now it's hard to evaluate, because he's successful relative to what? Successful in the sense that the neural net has done something? Plenty of them. Successful in the sense that nobody could think of a better way to do it? Not so many of them. Successful in the sense that you're surprised that a neural net can do it? Sometimes. Successful because it's a neural net? Sometimes not. I'll give you an example that is my favorite example of a neural net success that belongs to somebody else. I'll give you this example because I think it illustrates something. It illustrates an extraordinarily powerful and not widely known technique that can be massively important in learning. This was some work done at Carnegie Mellon University some years ago. And the problem was to drive a truck down an asphalt road at 50 kilometers an hour automatically. So the system that they built, the Alvin system that they built, had a camera that produced light intensities that were viewed as the inputs to a neural net. And the output of the neural net was turn left or turn right. To one degree or another. So you can imagine, okay, you can imagine wiring up a neural net that would do that. Here are the inputs. They have various values just like those X's do. And then there's an output. If it's greater than 0, you turn right. If it's less than 0, you turn left, and you turn left or right in proportion to the size of the output. And you can have a human drive the car down the road to collect data, to train the net. Didn't work. It should work because ultimately what this kind of neural net is doing is building some templates for itself. They're kind of fuzzy templates. That's when you look at it and say, well, what kind of knowledge does a neural net have? It's sort of templates for what a standard asphalt road looks like at various angles. If the road is down there and I'm kind of tilted this way, then my neural net should say turn left a little bit, because the template that it's built says that if you see an asphalt road kind of going that way, then you turn right. Better not do that. Turn left. But it didn't work. Why didn't it work? Because humans are too good. Humans keep the truck so well aligned with the road, they weren't getting any good training data. They weren't getting a situation that looked like this, which the truck might get itself into when run by a neural net. So the data they were getting was always very close to looking like this. The data that they needed looked like this. So how do they get the data that looked like this? Well, of course, they could have had a maniac drive down the road, but they didn't have to. They didn't have to. Because they know about the geometry of the world, and they can calculate what this would look like if the truck were misaligned. So they got that training data by exploiting their knowledge of the geometry of the world. So they had a program that generated this view automatically from this view. And this is a powerful learning principle. Frequently, the difference between a learning system that works and one that doesn't is your ability to internally generate a rich set of extra training samples based on a model.
So you didn't even need to base it on tiny perturbations magnified. It was just based on a pure model.
Pure geometry model of, a perspective model of what things look like. Here's another example. We put pictures on the web and expect to be able to recognize stuff from them. It's probably the case that that would be impossible if we didn't have a model of the head that enables us to generate an understanding of what the person's face would look like from another angle. So basically your face is mounted on a cylinder. And because you know that it's mounted on a cylinder, you can imagine what it would look like if so slightly perturbed. And that gives you more than one view of the face, and more than one view, two views of a face are enough to calculate what it would look like at any rotation. So we may even exploit something like that extra model generation in face recognition. Who knows? But this is a long diversion, and before the morning is out, I do want to talk about support vector machines. So perhaps we better move on to them. I've said that the neural nets are function approximators because for every set of zeros and ones that come in here, or every set of continuous values that come in here, some set of continuous values or zeros and ones come out here, and then you can interpret these in order to do classification. So you have function approximation with classification layered on top of it. The support vector machine is going to be purely oriented toward classification, not function approximation. Purely classification. I said with these neural nets, and now it's buried under a layer or two of chalk, that you can think of a single neural net, a single neuron, as putting a line in a feature space, a two-dimensional feature space, or hyperplane in a higher dimensional feature space. The nearest neighbor method divides up a space. The identification tree method divides up a space. The neural net method divides up a space. And the support vector machine divides up a space. But now we're going to start with dividing up a space instead of with a technique. So the place we ended up is going to be the place we start from now. And this stuff, the support vector stuff, is rich in hairy math. But once again, I want to talk about the intuition and point to where the mathematical magic has occurred without dragging you through the mathematical details, which would take a week, because it took me a week to figure it out. But let us create for ourselves a space. It's a two-dimensional space. It's got a population of x's and o's, or pluses and minuses. Maybe I'll switch to pluses and minuses. The same thing. And the question is, how are we going to separate the o's from the x's? Well, one thing we might do is we might find the center of gravity of the two populations, draw a line in between, and construct a perpendicular bisector. That's not what we're going to do, but it's perfectly rational. Another thing we might do is we might choose to use do a lot of computation and divide the space up according to the nearest neighbors. Also rational. Doesn't turn out to be what we're going to do. We might decide that we're going to use the decision tree and end up dividing the space up along the coordinate axes. Perfectly rational. It's not what we're going to do. What are we going to do? We're going to do something that leads to such, that seems so arbitrary, yet leads to such wonderful mathematics that it wasn't discovered for 50 or 75 years worth of pattern recognition effort. Here's what we're going to do. It's only known for about 5 or 10 years to be a good thing. So here's a minus. I'll switch to plus and minus, God knows why. Here's a plus. And what I'm going to do is I'm going to choose a decision boundary that puts the biggest street, the widest street between the two populations. Okay? So let me put two x's in, just so this is different from a perpendicular bisector. You know, if you think about putting the biggest street between those two populations, you get something that looks like that. That's a wider street than some other street that separates the two populations. It looks like so. So my thesis is that the decision boundary that puts the widest street between the two populations is a good one. And then the question is, how can I find it? Now, some details. What's my decision function going to look like? Well, I'm going to say that what I'm going to do is to take my first street, I'm going to draw the median strip on it, and I'm going to consider a vector that's from the origin that's in the direction that's perpendicular to that median strip. And I'm going to call that vector W. Then I'm going to calculate for any particular place, some unknown spot, I'm going to calculate W times U. Here's the unknown. It lies right there. I'm going to take the dot product of W times U, add on some constant, and check to see whether that's greater or less than 0. That's going to be my decision function. I know u is an unknown point, and I'm trying to classify. I'm trying to classify u as either a plus or a minus. I want to use this vector w and this constant b to create a decision formula, decision function.
But W is perpendicular to the
And all I know so far is that w is perpendicular to the median.
And we haven't determined that that's a good orientation yet.
We don't know what street we need, so we don't know what the median is. But we say that once we've got the right street, our decision function is going to be based on w, which is a vector perpendicular to the median. In fact, we're going to insist on some other properties of w and b, in addition to the fact that w is perpendicular to the median. What we're going to insist on is that for all of these things in our sample set, in our training set, that this formula, we're going to insist that this formula it gives us values that are constrained in the following way. We're going to insist that w dotted with u plus b is greater than 1 for pluses, and greater than or equal to 1, and less than or equal to 1 for minuses. All right? So in other words, for any x in the population of sample x's, this formula is going to give us either 1 or a number bigger than 1. Similarly, for all the minuses, the formula is going to give us -1 or less than -1. So that in the street itself, that's a -1, pardon me. Yeah, that's important because in the street itself, I've got a kind of no man's land where the values will vary from -1 to +1. Okay?
W dot u plus b greater than 0 is a constraint?
No, that's the decision function. This is a constraint. I'm arbitrarily imposing this constraint. This is the decision function.
I can certainly imagine situations where no good street will exist.
Exactly. We'll get to that. Yeah. Believe me, we'll get to that because it's just amazing what this technology does for that circumstance.
Okay.
So what we're going to do is we're going to somehow use this constraint to generate to find w such that we can use w like so. But first of all, can we find such a w? Well, let's see. There'll be some of these x's and minuses will be actually on the curve. And when they're on a curve, you want the value to be exactly +1 or -1. So let's call this one x1 and this one x2. Those are examples of samples that are on the curves. And for those samples, these values are +1 and -1. Okay. So then we can say we can talk about a vector between x1 and x2, like so. And note that that vector, I want to change the geometry just a little bit, just to emphasize that that vector is not going to be in general perpendicular to the median strip. So there's a vector between x1 and x2. Now we have to haul out a little bit of calculus because I'm going to ask you to help me with the following. I want to ask you to help me figure out what w dotted with x2 minus x1 would be. Not exactly that. I'm also going to divide by the length of w. That makes this a vector of length 1. And I'm going to take the dot product of that with this vector from x1 to x2. So I've got a unit vector in that direction, directly across the street. And I've got this vector that spans the street, and I'm going to take their dot product. What's that going to give me? Remember what a dot product does? It projects down. So here's x1 to x2. I've got a unit vector in this direction. You remember that the dot product gives the length of the two times the cosine of the angle between them. So the dot product is going to give me this. Well, that's just the width of the street. So this is a unit vector. This is a vector that goes across the street. And when I dot these two together, it's going to give me the width of the street. Okay. What else is it going to be equal to? Well, hang on, because the pain will be over soon. We know that when we take the dot product of W with a vector and add B, it's going to be for any of the samples, it's going to be greater than or equal to 1, or equal to -1 on the street. So if we take W and dot it with this guy, it's going to give us something. And if we take W and dot it with this guy, it's going to give us something. And when we subtract the two, the B is going to drop out. And the ones are going to add up because we're subtracting. One's going to give us a -1, there's going to give us +1. So this is also going to be equal to 2 over the length of W. Okay, so why did I say that? Well, because here, let's actually do it. W dotted with x2 plus B is going to be equal to 1. W dotted with x1 plus B is equal to -1. So if I subtract one from the other, the B's drop out and I get 2. So I take W, I dot it with x2 and subtract W dot it with x1. That's what I've got here. And then I divide by the length of W and I get 2 over the length of W. As the width of the street. Now we're home. We've come home. Because I want the widest possible street. So I want to maximize that, which means I want to minimize that. Subject to that constraint. So now, there's an awful lot of mathematical hair there, but now if we just talk to ourselves, we'll be able to know what to do next. You want to maximize a function while at the same time honoring some inequalities. Anybody remember what to do? Nah, it's obscure, but if you take a calculus course, you stumble across it and then forget it. But what you do here is you use the method of Lagrange. You use Lagrange multipliers. This is a maximization problem under a set of linear constraints. Bingo, the knee-jerk for a mathematician is use Lagrange multipliers. And so once you say that, then you can do a whole lot of mathematical manipulation. Too bad for your side, you still lose. Because the method of Lagrange depends on linear equalities as constraints, not inequalities as constraints. So in the end, you can't solve the problem formally. You have to solve the problem with a search. It turns out that when you go through the math, what you discover is something that's extremely important, fundamental to the success of the method. What you discover is that W is equal to all of the samples, x sub i's, times constants. So in other words, the W is a sum, a linear sum of the samples that you provided. That's what you find out. So how do you find the C's?
Simplex.
The mathematics tells you that this is the form of the answer, but doesn't tell you what the C's are. So how do you find the C's? Hill climbing. But now, in contrast to hill climbing in the world of neural nets, the space that we're hill climbing in has a very glorious property. It's convex. That means that there's a global maximum. And that means that there are no local maxima. So you can't get stuck in this space. So one of the major problems of ordinary neural nets, the possibility you might get stuck on a local maximum, disappears in this formulation because there's only a global maximum, no local maxima. So a method that hill climbs in this space will never get stuck.
Can it still be computationally intractable though with lots of
The question is, can it be computationally intractable? It can be computationally challenging because you may have thousands, tens of thousands, or hundreds of thousands of training vectors. So there's a whole industry of people who have written programs for searching that space in order to find these values. And so how do you find these values? You go out and copy somebody's code, mine if you like. Because mine's copied in turn from somebody else who wrote a C program and I translated it into Java. But when you do all the math, all the hairy math, pages and pages of hairy math, what it turns out is that the things you need in order to do the hill climbing in this space are dot products of the samples. That's one important thing to note. All you need in order to find the C's are the dot products of the samples. So we'll drill that into your head because that's going to be fundamental to our step after next. Another thing you discover when you do this optimization is that most of the C's are 0. Only the C's that correspond to vectors that are in the gutters are different from 0. Okay. So in some sense, the vectors that don't end up in the gutters might as well not have even been there. Because when you add up the sum, their constants are 0. So the samples that end up on the street gutters are the important ones. These are the ones that dictate W. And when we know W, we've got the answer. So these are, in some sense, the vectors that support the decision function. So guess what they're called? They're called the support vectors. Hence the name support vector machine. So let's summarize. We have thought about all sorts of ways of dividing one population from another. We've stumbled across this mechanism of thinking of finding the widest street. We've monkeyed around with the formulation so that we insist that everything that's in one population be greater than 1 when it comes out of the machine, and everything that is in the other population is less than 1. And when we manipulate that a little bit, we get some inequalities as constraints that go along with a minimization problem that says we want to minimize the length of the vector W. So we've done, after all that manipulation, we've come down to a need to do a minimization problem under a set of linear constraints. Then more and more math, and what you discover is that the vector you need to build a machine is a linear sum of the vectors you've got, but many of the constants are actually 0. And in order to do the minimization, two important things. There's a proof that the space is convex, so you can't get stuck, and there's a demonstration all you need in order to do the climbing in that space is these dot products. So that's amazing. Let me show you how one works. Okay, there's a space population, simple population of 2 pluses and 2 minuses. And you can see instantly where the street is, right? So let's see if the machine will calculate it. So everything blue is greater than 1, everything red is less than 1, and there's a no man's land in the middle where you change from red to blue. There are 3 support vectors. The 2 minuses are in the gutter, and one of the pluses is in the gutter. Let's put some more pluses in, back here in the blue part, and see if it changes anything. Shouldn't, and doesn't. Let's put some more minuses in.
So the width of the gutter, is that just something that's predefined for your machine?
The width of the gutter, there's no width. There's no width of the gutter. The gray part is an artifact of my display.
Okay.
It's actually a single line. It's the line where you make the trans.
If you had 3 dots that were very close to collinear, that would be along the minus gutter,
Yeah.
they would have to be exactly perfectly collinear.
Otherwise, yeah. Let's actually, sure. Let's try it.
It doesn't really work terribly well with real data.
No, it does. I'm not sure what you mean.
I mean, it's unlikely for
Yeah, I put
arbitrary samples to be exactly collinear. We're almost always going to get probably only
Yeah, you can just miss
1
one.
point on the gutter.
Yeah.
It'll drop one of the points.
It'll just drop one of the points. Suppose I put a point right here
Yeah.
and do it again. All 3 points are close enough within a tolerance to the gutter to have shown up as support
there is
vectors.
a predefined tolerance. That's
Yeah.
what I was,
Yeah. Now, if I put another minus in here, now I'm going to change things because I still have to find the widest street. 2 of the vectors have fallen out of the street, and the street is now defined by the higher and lower of the 4 minuses. So let's keep monkeying around. Now we're making the problem harder because the street's narrower. Okay. Now we can make the problem even harder by making it impossible. I don't know, is that possible? Yeah, that's impossible. So the way this particular variant on the theme is set up is that there's a little tolerance for impossible situations. So there the red vector is inside the street. The system running as long as I've let it run couldn't find a solution. In fact, there isn't one. There isn't a straight line that divides the 2 populations. Okay. Now, are we ready for some more magic? Okay. You can draw a conceptual line under this because this is a complete package. This tells you a magnificent method for finding a way of separating 2 populations. And even if you can't separate them with a straight line, you can put a tolerance thing into your program and you get answers like that. But too bad for our side. As you say, the world isn't often like that, where things can be separated by a straight line. Damn. Let's see. In order to do the maximization, we need dot products, and then W turns out to be a linear combination of those things. In order to make a decision, we have to do a dot product. Dot products seem to have a lot to do with this. I'm going to file that away for a second. Then, gosh, anybody, mathematics, Fourier transforms? You all know about Fourier transforms. You don't need to know about Fourier transforms. I'm just going to use it as a metaphor. But do some of you know about Fourier transforms? What's a Fourier transform? Well, actually, it's the same as, in the old days when we didn't have calculators, we used to multiply numbers by taking logarithms, adding the logarithms, and then doing the anti-log, right? What do you do in a Fourier transform? Well, it's too hard to figure out how signals interact, so you do their Fourier transforms. You multiply the Fourier transforms, and then you take the anti-Fourier transform to come back. So it's not uncommon in engineering science that you have a problem expressed in one space, and you find that it's easier to solve it by transforming it into another space, and then you transform the answer back. You want to multiply 2 numbers, you take their logarithms and add over here, and you take the anti-logarithm, you never have to multiply. You want to find out what kind of signal comes out of a box, you take the Fourier transform of the impulse response of the box and of the signal, That takes you into the Fourier domain. You do a multiplication, and then you do the anti-Fourier transform to get back to the result. So often it's the case you go into another space in order to solve a problem. So you can do the same thing here. If you don't have a straight line in the space you start with, maybe you've got a straight line in some other space that you can transform into. So you have a vector x in the original space, and in the transform space you have another vector phi of x. And you can solve the problem in the other space. What do you need in order to solve the problem in the other space? Well, you know, in any space that you solve the problem in, all you need is dot products. And when you solve the problem in that space, all you need to find to do the decision boundary is dot products. So now comes the mathematical magic. All you need to know about the other space is what the dot products look like. You don't have to know what the actual transformation is. You don't have to know what phi is. All you have to know is what the dot product of two phis are. So let us call this k of x sub I and x sub j. That's going to be equal to the dot product of the transform vectors. So this may be something that's easy to calculate. And you could care less what the phis are because you never have to know the transformation. All you need to know is the dot product of two transform vectors. And that's the real magic of support vector machines. There are some functions you can use for kernels that effectively transform the original vectors into another space in which a straight line separator is more likely. Then you can do all of the decisions you need to do in the transform space without in the transform space and succeed. So let's try it. If you see down the right side there, we've got a bunch of buttons. One of them is labeled v1.v2 to the first power. That's the kernel function for the original space. We're just taking the dot products. Another space we might try is taking that dot product and squaring it. That effectively transforms us into another space for which these are the dot products. Then we can try to solve the problem in that other space and see what the decision boundary looks like in this space. So just like the log, just like the Fourier transform, we're going to go off in the other space, solve the problem, and see what the answer looks like in our original space. Now you'll note that we're losing here because we've kind of got two minuses and a plus in an awkward place. But that's no challenge. Let's try that. So it's a very curvy street, but it's a straight street in the other space. Now, try to burn that into your mind for a second, and I'll just change the space again. I'll do the cube and learn again. Sort of the same thing. Let's clear this up and start over. Let's put a little wedge up here, like so.
You've got like a bullseye of X's.
Yeah. Well, what I want to do is I want to kind of give you the admiral's dream. This is what every admiral wants, right? He's got all his ships in position to fire on the lead ship of the opponent. So let's see if we can solve this one. No problem. So this transformed space gives us enough flexibility to solve this problem. Well, hell, let's try something challenging. we got one of our ships in amongst the others. I'm too scared to try it on this. Try this particular transformation on this particular arrangement, because I may just blow my program out. It takes. I've set it so that it iterates for a long time if it can't find an answer. But let me use another transformation. Instead of a dot product, I'll use something called a radial basis function. It's just an exponent of the difference between two vectors. It looks a little hairy, but it's just a formula. It's just a formula. It's an arbitrary formula. Turns out it's an arbitrary formula that makes it equivalent to a neural net. Now let's learn this one. Didn't quite do it. It wasn't able to cover that that minus ship that's in amongst the pluses, and it didn't cover one of the pluses. So let's change the function a little bit and give it a little bit more flexibility. And so this is an accident of how I happen to plop the ships down. It turns out differently every time. It scares me to death that something will blow out. But in this case, it has produced a very pretty result. It's put in some streets that completely separate the pluses from minuses, even though the shapes are challenging, or impossible in the original space, but not impossible in the transform space. Now, this is all done, remember, with a convex space, no local maxima. So if there's a solution, it's guaranteed to find it. But, there's no free lunch exactly, because there's still a problem already familiar to us. Let me show you. This kernel function that I've used is basically a Gaussian style hill of some width, and I can choose the width. So I can use a transformation that puts a wide hill around each point, or a very narrow hill around each point. So now I've used a fairly wide hill, a too wide hill in the beginning, so I had to make the hill a little narrower in order to fit all the data. Now I'm going to make it very narrow. I think that's as narrow as I get. So basically, I've made my little hill so narrow that it's basically built a little shell around all of the examples. Does this have a name? It's overfitting. It's basically, I've given it so much freedom, it's wrapping a solution around each of the samples. And I get no generalization power out of that. The more I shrink it down, the less generalization power I've got, and ultimately I'm just returning the samples by rote. So you have to be a little concerned about that. But otherwise, you've got magic. You've got a method that's guaranteed to converge. You've got a method that puts things in other spaces if you find you can't solve the problem in your original space. And these other spaces, by the way, can be characterized as higher dimensional than the original space. So if I were to back up now and look at this from a distance, what I would say is that this allows us to win by taking an intractable problem and putting it into a higher dimensional space where it is tractable. Okay? And that's the magic. That's it. That's how it works.
This can do everything neural nets can do?
You can choose kernel functions that make these things equivalent to various kinds of neural nets. This exponential kernel function I used in the final demonstration makes this exactly equivalent to a radial basis formulation of neural nets. And there are other kernel functions that makes these sorts of things equivalent to other kinds of neural nets, but with these additional properties that are highly desirable. So why talk about this? Not because it's done by AI people, but because it solves the kinds of problems that AI people are likely to be expected to be able to solve. It gives you an alternative to the knee-jerk over toward a neural net as a way of solving a problem. And this is a way of solving the same kind of problems in a way that's much more not merely mathematically satisfying, but likely to win in a practical sense. So these things, there's still a great tidal wave of literature coming down showing how these things can be applied to this problem or that problem that used to be solved or that people used to think of as ripe for neural nets or some other mechanism of that sort, but they're done better with these support vector machines.
Is this in the text?
No, it's too new to be in the text. Yeah. But by the way, you can play with this online. I'll send a URL around. We have.
You're going for a new edition of your text?
Am I going for a new edition to my text? I'll talk about yes, and I'll talk about what will look like this afternoon.
You mentioned yesterday something about support vector machines demonstrating sparseness as a property.
Yeah.
And I
Yeah.
just wondered if you could.
Yeah. It's also sparseness and high dimensionality are opposite sides of the same coin. If you take a bunch of points in a two-dimensional space and somehow blow them out into a 100-dimensional space, then they're sparse in the higher dimensional space, and even though they're dense in the low-dimensional space. So when you go to a higher dimensional space, you expect more sparseness, and you expect it to be easier to put a plane between them. So that's actually that's the fundamental insight. The fundamental insight is, if you've got a problem that's hard to solve in a space, try to put it into a higher dimensional space. And in some sense, that's where we should start, because this is merely a kind of apparatus for getting you from one space into a higher dimensional space in such a way that you still know what to do. I mean, God doesn't usually help us out like this, but in this case, the mathematics works. You know, we spent a lot of time in a calculus class learning how to integrate stuff. And it turns out that almost nothing's integrable. So it's, in some sense, a waste of time. It's only a lucky accident when something actually can be integrated. It's only a lucky accident that every once in a while the mathematics goes all the way through and produces a fabulous result. And this is an example where it does. Okay? Okay, so that concludes the morning.